Dalagata, who will tell us about new facts on classical and quantum inequality supergraphs.
Okay, so thank you. I'd like to thank actually the organizers for inviting me here, and of course all of you for staying until the last session of the conference and of the workshop. So what I'm going to talk about is based mainly on three papers. One which was actually an assignment for the master thesis of Gianluca Inverso, who was my master student and who now is a PhD student in Rome and is already published. Another paper which appeared a month ago or so with Fabio Zwirner, which is on the quantum part, let's say, and some work in progress which I hope will be out very soon in the next few days, again with Gianluca Inverso and with Mario Trigiante at the Turin Politecnico. So for the classical vacua part, actually, we've heard already yesterday in one of the parallel sessions something about it because there's been some related work by the group in Groningen, Di Bitetto, Guarino, Rust, Borghese, Linares, and therefore I will actually comment on that too. So why should we be interested in n equals a supergravity, and why n equals a supergravity again? I mean, we know that n equals a supergravity has been used in the 80s and tried to be used in the 80s to extract some phenomenology as a unified framework for gauge interactions, and we're at the string phenomenology conference, so at some point there should be some phenomenology out of this too, but we know that n equals a supergravity fails for that purpose. However, as you may know very well, it is again at the center of many investigations because of various reasons. The first of which is the fact that n equals a supergravity is finite up to 4 loops, and it may actually be finite to all loops. And of course, even though this is a perturbative statement about the ungauged theory, of course doesn't really mean that that we could use n equals a supergravity as an effective full quantum theory of gravity. Still, it would be interesting to understand better what is the role of supersymmetry in these cancellations, and whether the cancellations that appear that make this theory finite or possibly finite have to do just with supersymmetry or with something else. And the interesting point is that people think and discuss about n equals 8 ungauged supergravity, where obviously you have only essentially, you're expanding around a Minkowski vacuum, the natural Minkowski vacuum around which you define your theory. But actually there are other deformed gauge supergravities, n equals 8 gauge supergravities, which have a Minkowski vacuum, on which you can still think of trying to perform your perturbation theory and see whether the theory is still finite or not. And I will come back to this later on. Then another main line of research in which n equals a supergravity may play a role, n equals a supergravity in 4 dimensions, is the gauge gravity correspondence, because we know that the ADS vacua in n equals a gauge supergravity may be related to dual field theories, which may have applications as 3-dimensional theories to condensed matter or other systems. And of course, if you know and you classify all the vacua of n equals a supergravity, you may know and learn something about the dual field theories. And then the reason why I started looking at n equals a supergravity again is actually has actually to do with the landscape of stringy vacua, and the fact that it's very difficult, as we've heard also during this conference, to find de Sitter vacua, stable de Sitter vacua. And even if in n equals 1, in the n equals 1 theory still, even if it's difficult, you may find a number of stable de Sitter vacua. In gauge supergravity with more than one supersymmetry, this becomes more and more difficult. In n equals 2 we have one example, and in n greater than 2 we have no examples at all of de Sitter stable vacua. So the point is, we would like to understand why it is so. Why in supergravity already it is so difficult to obtain stable de Sitter vacua, positive cosmological vacua with a positive cosmological constant, which are also metastable at least, when you have more than one supersymmetry. Why does supersymmetry hate so much a positive cosmological constant, and as we will see, even a zero cosmological constant, even though that may sound surprising? In fact, as I mentioned a while ago, this discussion about the finiteness of n equals a supergravity, which is done for the ungauged theory, could be done also for the gauged supergravities if you have and you can provide other Minkowski vacua around which you can perform this perturbation theory. The fact is that for more than 30 years, we had only one way to get Minkowski vacua in gauged supergravity, and that is spontaneous in n equals 8, in the n equals 8 theory at least. And that is the Scherk-Schwarz mechanism, which of course you all know in the context of string theory and even in supergravity when you think about dimensional reduction, and which from the n equals 8 supergravity point of view is just a specific gauged supergravity model, which has a specific gauge group, which is this U1 cross T7, where you gauge a U1 and some translational isometries, and where the masses of the various fields are just classified by the charge matrices of the various fields with respect to this U1. This model, which is the only model that we had for more than 30 years, has some interesting properties. The first of which is the fact that you can, because of the group theoretical structure that you have underlying it, you can compute the supertraces. I will come back to this later on. And you can show that the quadratic, quartic, and 6th power of the supertrace is vanishing, while the first non-vanishing is at the 8th power. And this implies, on the other hand, that this theory is one-loop finite. And also, you can compute the one-loop effective potential and see that the one-loop effective potential becomes negative. So that even if you start from a Minkowski vacuum, where supersymmetry may be broken from n equals 8 to 6, 4, to 0, and then in this case, of course, we're talking about really the n equals 0 case, you see that the one-loop effective potential becomes negative, and so you don't preserve the vanishing energy of your vacuum. And actually, it's also going in the wrong direction somehow, no? Because you may think that you may have in mind a scenario in which you start from Minkowski vacuum and then quantum correction would generate the cosmological constant that you need, but what you see is actually that the direction in which this is going is exactly the opposite. Still, this was just for one model, the Scherk-Schwarz model, which is a very nice mechanism, but it's just one particular gauging in n equals 8. And as I said, for 30 years, this was the only thing we had available. But what I will show you in this talk is that now we have many more new examples, and we can then make new and more general statements about n equals 8 supergravity. First of all, with our analysis, we have found many new classical properties, which is we found that actually, as we will see, the classes of gauge supergravities that you can have, the classes of model, is much larger than what we expected. We know that they are classified by 912 parameters, as I will discuss later on, but the kind of theories that you can have is much larger than expected, and especially if you want to try to interpret these theories as coming from M theory or string theory, we will see that these new classes of gaugings that we found are actually rather problematic, and they pose interesting questions. Then, as I said, we have a method that, well, it's not really new in the sense that this was used, it's been used a lot in the past in theories with less supersymmetries, but it's the application somehow that is new, that allows us to find many new vacua of this theory, among which many new Minkowski vacua. We actually now can produce easily hundreds of new vacua of these theories. Of course, the purpose is not just to produce vacua like that, but we want to understand then the properties of these vacua. But of course, if you start building certain systematics, then you may understand also the reason why you have certain properties. And then I will discuss in the second part the quantum properties of this theory, because now that we have these results, we could check the one-loop finiteness, at least for the superpotential, and the supertrace relation for a generic model. Not anymore just for the Scherk-Schwarz model or for the 4, 5, 6, 10 examples that we find and that we build that have Minkowski vacua, but actually we could prove in general that for any gauge supergravity, which has a Minkowski vacuum under certain conditions I will discuss later on, the potential is one-loop finite, and in all the known examples that we have built so far, it actually becomes negative. So it seems that this is a generic feature of n equals 8 supergravity. And in some sense it is disturbing, but it is also rather interesting. So the first part, as I said, is about the classical properties. And let me start directly with the results somehow. Since the 80s, people tried to construct gaugings of n equals 8 supergravity and finding vacua. And in the SO8 models, a number of vacua have been found immediately, essentially. They are all vacua with a negative cosmological constant, but they have different numbers of supersymmetries, which depend also, of course, on the gauge group, on the residual gauge group. And as you can see in this list, the gauge groups are always quite large, and the fact is that in n equals a supergravity you have 70 scalar fields, so the potentials are rather intricate. And in order to find this vacua, to find minima of the gauge supergravity that people were studying, what they did was to impose that the vacuum had a certain large symmetry group, so that you could set to 0 the scalar fields which are not singlets with respect to these symmetry groups, and that's why we have a list like that. Now,
are they stable?
These ones, if I remember correctly, they are all stable, but there are some which are stable, some which are not, and I will comment on this.
Vacuum, you don't need,
okay, so far I made only critical points, then I will discuss stability, and in fact this is the other example. So they found also other models, not just, they didn't analyze just SO8, they analyzed also models with other gaugings, in this case for instance SO3,5, SO4,4, or this which is a contraction, which is just essentially a special Scherz-Schwarz compactification, where you can find also 0 or positive cosmological constant. However, in this case, indeed, the vacua are not stable. But there were very few examples. And now, more recently, Fischbacher started to do an analysis, a numerical analysis of the vacua of SO8 gauge supergravity, so a specific model, and he found many new critical points, of course, with all the limits of the numerical approximations, of course. But in order to really understand how these vacua are distributed and what are their properties, we would really like to have analytic solutions. Now, with the method that I will explain in a while, we can easily identify many new vacua. As I said, we can produce hundreds of them now. And not only just the vacuum, but also to compute rather easily the full spectrum of the theory around this vacuum. And this is also something that was missing for many of the vacua that I showed you before. So they were found already in the 80s maybe, but they didn't have the full spectrum. So in some cases they couldn't even establish really whether they were stable or not. Now, I will not give you the list of all the vacua that we found, of course, but these are just some examples. And I want just to focus on a couple of them because they are interesting. So the first thing is that, as you can see, you have many different groups. You can have semi-simple gaugings or more complicated gaugings, like these ones here. And given also the intuition that you can build from looking at examples in with a lower number of supersymmetries, you would expect that the Minkowski vacua could be found with gaugings of this sort. Whereas what we found, much to our surprise, is that we could find a Minkowski vacuum which is stable with a semi-simple gauging in the SO6,2 gauging. And also these examples that I wrote here go beyond the so-called exhaustive classification. I mean, there are some papers which have exhaustive classifications of gaugings in n equals a supergravity, which were not really exhaustive. And so you can find new gaugings which give you also many new vacua, which may be interesting indeed.
Do they have, sorry to interrupt you, but do they have typically flat directions?
I'm coming to this. You're anticipating my next slide. So this is a list now of the, as I said, I can not just compute the vacua, but I can compute the full mass spectrum, and so I can understand exactly, address questions like the one that Jan was asking right now. And you can see from this table, I don't want to enter in all the details, but just to show you some features of this vacua. And one thing is that indeed, I mean, when I'm talking about stability here, I mean that at the quadratic level you don't have any tachyon, but you can see that you have many zero eigenvalues. Some of these, of course, are just the goldstones of the gauge symmetry that you broke, but others are really flat directions, and these constitute an interesting moduli space for these compactifications. Of course, you have examples which are stable. We have examples which are not stable. For this ITER, for instance, we still do not have an example which is stable, but we're making progress in that direction too. I mean, at least in understanding why it's not coming out. And then we have many other examples. Now, the other thing that I want to show you about this table, that I want you to notice in this table, is the fact that no matter what is the original gauging, the mass spectrum that we find at the end depends only on the residual gauge symmetry group. Now, one thing is obvious, that the scalar fields on the vacuum will be multiplets of the residual symmetry group. So you would expect that the number of fields that have a certain mass will be related to the representation in which they sit with respect to the residual symmetry group, and so in some sense you would expect that indeed it doesn't matter much on the original gauge group. But the surprising thing is that not just the number of fields which have the same mass have the same structure, but even the value of the mass is the same. So for instance, for ADS vacua or de Sitter, where you have a cosmological constant, if you compute the ratio of the mass over the cosmological constant, you find that all the models that have the same, for instance, SO6 residual gauge group have exactly the same numerical value for the masses. So the masses are completely fixed by the residual symmetries, and this is something that we don't yet fully understand. The other interesting thing is about the flat directions. These vacua typically have a rather non-trivial and interesting moduli space. For instance, here I plotted the value of the mass for two of the various moduli that we have in the SO6, 2 gauging. And of course, there is one point which preserves SO6 cross SO2, but then changing the values of these moduli, you may break further the symmetry, and depending on how you break it, you may actually generate some instability and get some tachyonic direction, but in other directions, you may actually further lift some of these degeneracies. But the interesting thing of these moduli space is that if you take the limit towards the boundary of the moduli space of this SO6, 2, you see that at the boundary you get exactly the same spectrum and interactions that you get in a Scherk-Schwarz compactification where all the mass parameters are set equal. So for some reason, it seems like that you have, on the one hand, a moduli space, which is the moduli space of the SO6, 2 gauging, and at the boundary space, this is touching the moduli space of the Scherk-Schwarz gauging. So this is suggestive of the fact that if this comes from some higher dimensional theory, maybe, and you can interpret these moduli spaces as volumes of your internal manifold or things like that, the complex deformations, there is something happening at the boundary of this moduli space. Now, how did we get this vacua? And as I said, we used actually an idea which is rather old and simple, and it is the fact that we can use the structure of the scalar manifold, which is a coset space, and the symmetries that it has. And by means of that, we essentially rewrite the minimization equations for the potential in terms of algebraic equations which are at second order rather than non-polynomial and complicated equations. And the way to do it is the following. So if you take the scalar manifold of n equals a supergravity, which is E77 over SU8, which has 70 scalar fields, you can try to parameterize it by using a coset representative or an invariant parameterization like this one, so that the E7 action is linear. And then the potential, which defines the masses then of your scalar fields, depends on this combination M in a simple way, as you can see here. And of course, it depends on the structure constants of the gauge group that you made local in the theory. Now, as you can see in this potential, obviously, the scalar fields will appear in a very complicated way, but the structure constants will appear always quadratically. So minimizing the potential may be complicated, but if you use this fact that the scalar manifold is a coset, you can actually simplify it. And you can actually relate it to a construction that has been put forward in the last few years, which is very effective, which is that of the embedding tensor, and impose essentially and translate the minimization conditions on the so-called embedding tensor. What is the embedding tensor? The embedding tensor is essentially a tensor that defines for you the full gauge supergravity, and it's nothing but the tensor that tells you which of the E7 generators becomes local. You have an E7 symmetry in principle in your theory, and you make some of these isometries of the scalar manifold local, and the gauge generators are simply defined by that. Of course, you cannot pick any arbitrary subgroup. You can pick at most a dimension 28 subgroup, because of course you have 28 vectors at best. And still you would have that you could use both the electric and the dual vector fields, and this tensor is sitting in a representation which is the product of the 56 and the 133-dimensional representation of E7, so it has many, many degrees of freedom in principle. But then consistency, which means essentially gauge invariance and supersymmetry, are going to tell you that some of these representations cannot be there, and then you're left with only 912 parameters. So essentially, the gauge supergravity is defined by some of these 912 parameters. So it's defined by the embedding tensor, which has to satisfy some linear and quadratic constraints. Now, after you have that, you could try to minimize the potential. The potential, as I said, is a combination of these embedding tensor, of the structure constants, and the scalar field via their cosette representative. However, you see that the action of E77 is linear on both, and because of the way they are contracted, you can see that you can actually undo any change of parametrization on the manifold just by doing an inverse change on the embedding tensor. What does this mean? It means that you can span the whole scalar manifold for a given gauging just by looking at one point of the manifold, the base point, where you set all the scalar fields to 0, and instead of scanning for vacua on the moduli space, you scan over all the possible embedding tensors. So essentially, you simplify the critical point conditions, looking at the critical point condition only at the point where all the scalars are vanishing, so that you have a quadratic condition on the embedding tensor, and then you scan over all possible embedding tensors which satisfy those conditions. So instead of having 70 complicated non-polynomial equations, you just have quadratic equations on the embedding tensor. And this is what allowed us to find these solutions, and not just us, as you can see, and as I mentioned before, a similar approach was also used by Di Bitetto, Guarino, and Rust. Now, another thing you would like to do once you have this vacua is to try to understand the string theory uplift. And of course, for the SO8 gauge supergravity, we know that you can produce it by compactifying M theory on the 7th sphere. Now, that's obviously a geometric compactification. All the other deformations, I mean, and as I said, there are 912 such deformations, can be organized, for instance, from the M theory point of view in this fashion. And you can see that in here, in this table, you have the 7-form flux, the 4-form flux, the deformations that you would interpret as geometric fluxes coming from deformation of the torus. You imagine first to obtain an N equals A supergravity by compactifying on a torus and then deforming. You have other fluxes which you may interpret as locally geometric fluxes, but then you have many other fluxes which do not have an immediate interpretation. I would also like to stress the fact that actually, even though many of these are called non-geometric, it really depends on the framework you have in mind, because for instance, the 7th sphere compactification gives you a flux which is sitting in this representation, which of course is not geometric from the point of view of deforming a 7 torus, but that's because the 7th sphere is not simply a 7 torus which is deformed. Now, what we did was to focus on some of these for simplicity, and just to scan the theories that you can find which are consistent in the vacua which appear in this sector. So we choose these two embedding tensor which have a constraint which comes from the quadratic constraints on the embedding tensor, and looked at the theories that you can find. And here is the first big surprise. You know that when you think about SO8 gauge supergravity, you think that this is a unique theory. It's the theory that comes from the 7th sphere compactification. However, you can produce SO8 gauging for any value of the C parameter which interpolates between these two embedding tensors. So you have an infinite class of SO8 models. Now, the first thing you would think is that these models are just one dual to each other, using some duality in 4 dimensions. But then you can check that this is not the case, not for all of them. Just like it has been done, for instance, for black holes, you can define invariants. For instance, for black holes, you could define quartic invariants which depend on the charges of the black holes. And of course, objects which are dual to each other should have the same duality invariant. Now, for the embedding tensor, this is more difficult because you cannot easily find scalar invariants, but you can use so-called tensor classifiers, which have been put forward by Trigante and collaborators. And what we found is that you have an equivalent model for all the values of C which are between 0 and 1. So we have an infinite number of SO8 gauge supergravities, and if you look at the vacua of these theories, they are different. And this, of course, is rather interesting and deserves an interpretation from the high-dimensional point of view. So summarizing this part, I hope I convince you that we have a new method that allows us to find many new vacua, and which gives us some interesting and raises important questions in understanding this n equals a supergravity. The fact that the masses are related to the residual gauge group, the fact that we have this interesting modular space, and these new infinite classes of gaugings which do not have a higher dimensional origin that we can understand. Now, in the last few minutes, I would like to switch gears and change gears and discuss a bit the quantum properties, because these are also very interesting. As I said, the ungauged n equals a supergravity is finite up to 4 loops, and possibly more. Of course, when you gauge the theory, you introduce new couplings. So you cannot just take the results that you have in the engaged theory and say that they apply to the gauge theory. However, you can see that, for instance, the one-loop divergences are controlled by the supertraces, which are nothing but the sum of the masses of all the states that you have in your theory, weighted with the number of degrees of freedom that a scalar, a vector, or a spin 1/2, spin 3/2 field carries, and a sign which depends on the fact that this field is bosonic or fermionic. And the one-loop effective potential, I'm sorry you don't see it very well here, but anyway, the one-loop effective potential depends on these supertraces for the divergent part, and not just for the divergent part, but also the finite part depends on this certain combination of these supertraces, of these masses. And of course, in a supersymmetric theory, the supertrace of n to the 0 is just counting the bosonic and fermionic degrees of freedom, so it's vanishing. But you have a quadratic divergent, which is proportional to the quadratic supertrace, and a logarithmic divergent, which is proportional to the quartic supertrace. So if you can prove in general that the 0, second power, and fourth power of the supertrace is vanishing, then you know that the one-loop effective potential is finite. And you can actually then try to compute it. And what we showed is that you can actually prove in general that the quadratic and quartic supertrace mass formulae are vanishing. Just by using the fact that you want a critical point which has vanishing cosmological constant, and you use the consistency constraints that I've discussed before, which come from this embedding tensor formalism. So just by using that, you can prove that the quadratic and quartic supertrace are vanishing, and this means that now we have that the one loop effective action is finite, not just for the particular models which we found which have a Minkowski vacuum, but for any n equals 8 spontaneously broken Minkowski vacuum. Then, if you analyze better the models that we have, you can see that once again the masses are fixed with respect to the charges of the unbroken U1 factors, which is also something that we don't understand fully. However, this means that in that instance, in those instances, you can find all the values of the various masses of the fields explicitly, very easily, and write down a general formula for all the masses of the fields. And by that, you can first of all prove that also the sixth power of the supertrace for all these models is vanishing, and compute the explicit value of the eighth power of the supertrace, and you could compute all of them. And you can compute, of course, then the one loop effective potential. And what you see is that once again, the one loop effective potential is negative. So for this one, unfortunately, we don't have yet a general proof which does not depend on the model. We have only a proof that depends on the models that we found. But so far, all the models that we found still satisfy these conditions.
This is valid all over the field space, or only at the critical point?
We're talking about the critical point, then you have moduli. But even if you move along the moduli, then you still find this condition. No, it doesn't valid. Of course, if you're moving away from the critical point, then the theory is not finite anymore. You start getting divergences in general. So the summary of this part is the fact that the quartic and quadratic supertraces are vanishing for any gauging that leads to a Minkowski vacuum. So it's not just something that was there in the Scherk-Schwarz compactification because of the special property of Scherk and Schwarz, but it's something that is really intrinsic in the construction of n equals a supergravity. Then, as I said, the one loop potential is finite, calculable, and unfortunately is negative definite. So in the end, this means that supersymmetry is pushing somehow the value of the cosmological constant to a negative value. And again, we don't have yet a general proof for the second part, but it's rather interesting that somehow supersymmetry doesn't not only hate a positive cosmological constant, but even the zero cosmological constant, as soon as you start computing quantum correction, gets corrected to a negative value. Of course, this is n equals a supergravity, but n equals a supergravity is a well-defined constraint theory which can be used as a toy model precisely to try to address and understand this question, which maybe have an impact then on more general theories which come from string theory. So I rushed a bit through the various results that we had, which were quite a lot, both at the classical and the quantum level. Of course, there are still many things to do, and we're still working on this. There are many more vacua which can be found. As I said, the purpose is not just to find vacua, but to try to produce enough vacua that we start getting an understanding of why we get these properties. And of course, the interest now is in focusing on the de Sitter vacua to try to understand better why it is so difficult to get them. Then, as I said, for the mass formula that we have and the one loop instability, so far we don't have a general proof. We have a case-by-case example which works, but we would like to have a better and general understanding or to find some counter-example. Of course, another important point is that of the string uplift, and as I said, the SO8 gauge supergravity, the new infinite classes of models that we found is problematic. It's problematic, especially from the dual point of view, from the gauge, from the gauge theory point of view, and we would like to have a better understanding of that. And eventually, the purpose of the whole thing, which is what made me start looking at this n equals a supergravity again, is still there. It's still on the table, and it's the fact that we would like to really understand the nature of the obstruction to having a positive, or as I said, in this case, even zero cosmological constant. And I hope that by this kind of analysis, we will get a better grasp on it. Thank you.
Thank you very much. We have time for questions.
I have two questions. May I? So the first one is related to the spectra with of vacua with the same residual gauge group.
Yeah.
So you said that there are zero modes, which are the Goldstone, right? So is it possible to go beyond the second order and check whether maybe these zero modes have different higher order corrections for different...
Yes, well, they do actually. That's the interesting thing. If you look at this table, as I said, if you look at the residual gauge group, the quadratic the potential at the quadratic level around the critical point is the same. The spectrum is actually, what I can tell you is even more. Not just that this is the spectrum of the scalar fields. We checked even the spectrum of all the other fields, of the vectors, fermions, and so on. And you can see that they have exactly the same spectrum. Still, the potentials are different. You can check that. We didn't check for all the examples, honestly, but we looked at some of the examples, and you can see that beyond quadratic order, the potentials changes. So it's...
And the second question is related to the, you have these three conditions in order to prove the result for the one loop. So the criticality, quadratic constraints, and vanishing of the cosmological constant.
Yes.
Did you try to relax some of these? So for instance, what happened?
For instance, if you already take a non-vanishing cosmological constant, you can see that the supertrace is already the quadratic supertrace is non-vanishing. We actually thought about trying to use that as a constraint on the possible values of the scalar fields for a positive cosmological constant, so the other way around. But unfortunately, you get very weak constraints, so it's not too useful also in that direction.
More questions, please.
So in order to, so the embedding you use is GL7, right? To make the connection with M theory.
Well, that was, an example. Of course, you can try to do other embedding.
Do you understand all the fluxes in M theory, or?
Not really, no. I mean, some of these, well, you can further relate these to of course, for instance, type 2A, and so some of these which may look, again, non-geometric in this setup. They may become geometric when you do, or locally geometric when you do the reduction and so on. But I mean, it really depends on the frame. This is just one choice. In this frame, some of these look geometric, some others look non-geometric. But as I said, it depends also a lot on the fact that you are thinking about this as a reduction on a torus and try to deform the torus, because, for instance, for a 7-sphere, this is completely geometric. So,
More question? If not, let's thank John Guido again.